Hi everyone. Uh, Today we are going to look at an application of lists. So we have looked at the array-based implementation, then we actually implemented it using linked lists. We briefly looked at the variants of singly linked list, that is doubly linked list, as well as circular lists. One of the applications of lists is what this uh, lecture is about. And here we are going to implement polynomial abstract data type. And that is, uh, yeah, that is going to be the topic of today. Just give me a minute. Right. So, the polynomials is actually a very generic entity which can encompass multiple aspects. But what we are going to be restricted with for this discussion is polynomial in only the sum of the x values, right? So there is a um, combination of uh, some coefficients ai, and then there is a variable x whose different degrees are going to be part of this polynomial multiplied by these coefficients, and a summation over all of this from 0 to n, that is x power to I, are going to be essentially the terms that are going to define this overall polynomial. So the function of that variable x is, so when I equal to 0, essentially it is a0, that is some constant. So a0 plus a1x plus a2x square plus a3x cube, etc. So all of these are going to be the evaluation, right? And all of these xi's, all of these ai's coefficients could be integers or floating point values, etc., depending upon your application demand. Now there are multiple operations on these ADTs, right? So we solve these when it comes to 0, or we can possibly have an inequality which deals with less than equal to or greater than equal to, etc. Things. But that is not, the solving is not really currently our concern. Our concern is primarily to represent these ADTs. So how do you think about representing this given a particular abstract, given a particular polynomial? How do you represent it? This can be nicely modeled using, for example, arrays, and that is a natural thought that comes to your mind, where we can have index 0 storing the value of a0, index 1 storing the value of a1, and so on. And that suffices for our purpose, assuming that you know the largest n. So this seems to be a reasonable approach, and this will work, and we'll be able to perform certain operations with polynomial ADTs. Right? So there will be some operations which we will do on the polynomial ADT. For example, we can insert a particular xi. Right? So if I say that given a polynomial, now add, let's say 5x to the power 6. Right? So this number I want to add. So in such cases, I mean, these are some of the insertions, and I can as well think of removal of a particular term. Why would this insertion and removal come into picture? Is because we can perform a higher level operation of, let's say, addition of polynomials or multiplication of polynomials. So, and there could be other operations, just that currently we are just concerned about a couple of these. So you are given this polynomial, and then another polynomial, you want to add them up, and that is going to change the degree of the highest degree in some cases, and that is going to change the coefficient. So we can definitely implement this using an array where the coefficient is going to be possibly changed. And if there is a new coefficient which is coming up, let's say I'm inserting a particular, like I said, 5a to the power 5x to the power 6, then maybe initially there was no power of 6 element present. So now I can just, so it was probably 0, right? So in the array, we'll initialize with 0, and now the x to the power 6, and therefore sixth element I'm going to set the value 5, which defines the coefficient of that particular element in this polynomial. So all of this seems to be good, and array-based implementation also seems to be all right for this polynomial representation. So let me move ahead. So like I was saying, this is one example of a polynomial which can be represented nicely using this ADT. What are the member functions that we would like to have, right? So this is something which we have to think about when we decide to implement this polynomial abstract data type. So some of the functions are initialized. So what is initialization? Initialization could be that you actually give all these coefficients from 0 to whatever n. Alternatively, initialization just be initializing it to an empty polynomial, and then using certain functions like set a particular coefficient for a particular power, we might be able to then actually create the polynomial. So initialization might just be empty polynomial, right? So that could be your design decision depending upon how you want to implement. This might turn out to be handy for us, initialization as zeros and setting a particular coefficient, because then we can as well create the variable as well as insert a particular one, which can be very useful for us when we perform the operations on polynomials, which is let's say plus or multiplication. Like I was saying, adding of polynomials, multiplying of polynomials. So these are different member functions which we are currently interested. Definitely there are more operations that we can do and define. Right? So okay. So now the question is, we can implement it using arrays, which we discussed nicely, and that seems to be a reasonable implementation. And then there is a possibility that you can as well implement it using linked lists. So you can have this particular example, x to the power 4 minus 4x cubed plus 7x minus 6. This can be represented as, at the 0th element in the array, we store minus 6. At the index 1, we store 7. At index 2, we store 0. At index 3, we store minus 4. At index 4, we store 1. Right? So that is how the representation, array-based representation is going to be. And exactly the same thing we can copy when we are dealing with a linked list. So you can store these 5 nodes, and that is going to represent a linked list. That is going to represent the polynomial. But there is something more which you can do at this stage, and I suggest you pause this video and think about what other optimized implementation you can do with respect to when you think of implementing it as a linked list, for even the example that is given here. All right, so assuming that you have thought about it, whether you got the answer or not, but it's important that you thought about it. Okay, one suggestion is that x to the power 2 is actually not present in this polynomial. And then why do I want to really store that 0 in the linked list? In the case of arrays, I don't have a choice. I have to represent it because I'm indexing it using the polynomials, that variable's power. But in case of linked list, since I have to, okay, so that is one way. If I have to get rid of storing this square, then there is another difficulty which is going to come up. And we'll come to quickly why not storing certain terms might turn out to be beneficial. And you should definitely think about that before we move further. But yeah, so storage is definitely one aspect, but then the computation also becomes easy if you do not have certain terms available inside the linked list, such as adding of polynomials. Then I don't have to worry about, okay, I'm adding 0 to 0, right? So that is not really required to be done. So when I am trying to now copy the array-based representation to the linked list, one thing that I don't need to worry about again is the index. Because like in arrays, the index itself was implicit. So in case of linked list also, if I am storing 5 nodes, minus 6, 1, minus 6, 7, 0, minus 4, and 1. If these are the 5 elements in this linked list which is representing this polynomial, then I don't need to store what is the power of that polynomial, the power of that particular element. So I don't need to say that the first one is 0, second one is 1, third one is 2, 4, 3, and 4. Similar to arrays. But now if I decide not to store 0 for x to the power 2, then I have only 4 nodes with me. And now I am forced to use this particular power inside the node. That means that I'm actually going to store minus 6, 0, 7, 1, minus 4, 3, and 1, 4. Right? So that is how my 4 node linked list is going to look like for this particular polynomial. Is that going to be useful? May not be, because we try to reduce essentially storage in turn computation also. But maybe I'm going to require 8 elements rather than storing only the 5 elements. Right? Which means that there is some trade-off which is involved, and we might be able to think about under what conditions storing it as a linked list having those only the non-zero elements, whether that is helpful, or storing as an array having even the 0 elements, whether that representation is storage wise helpful. Right? So this is a point which you should pause the video and think about for different kinds of polynomials. Okay, so the first classwork that you need, I mean, this is not probably a classwork, this is offline classwork, I would say. Create a structure or a class to implement the polynomials. Right? So think about these different operations, how you are going to represent it, either as an array or a linked list. And based on that, you have to decide what variables should be part of this structure and what member functions will be part of it. What will be the signatures of these member functions as well. Some of those might return something, some of those may not. What are the parameters that these individual functions will take, etc. Right? Also, you can think about a constructor, right? So that initialization is there. So you can either have an init function or you can have a constructor. Okay, sounds good. And since we are creating a linked list, maybe you can as well have a destructor which will deallocate the memory for all of this. Sounds good. So now, assuming that you have thought about it, about the disadvantages of the using arrays, think about representing this 2 to the power 2 into x to the power 1000 minus 6. This is my polynomial. Now if I have to store it using an array, the way I'm going to store it is for 0th index, I'm going to store 0. For 1th index, I'm going to store minus 1. And then for 2, 3, 4, I'm going to store all zeros. And then for x to the power 1000, that is 1003, is going to be 2. This immediately gives us the disadvantages of using arrays and not storing the explicit powers and coefficients. Coefficients anyway we have to store, but the powers we are not explicitly storing. And this can give you a clear indication that you might want to change this representation. So in such cases, it becomes very helpful when the skew is large, right? So think about it in this manner, that these are called as dense versus sparse computations or dense versus sparse representations. When almost all the powers of x are present, having a dense representation like arrays where you have all the indices present is going to be useful. But when the polynomial itself has very few entries and not all of them are really nearby, then it makes sense to have a sparse representation which is actually keeping track of exactly the powers which are present rather than storing for every power which might be present, might not be present as well. So this is where the sparse representation comes into picture for the polynomial ADT. And that can be nicely done using a linked list where you will store the first node as -1, 1, and the second node as 2 and 1000. You can as well reverse it, but you will see that there is an advantage of storing it either left to right or right to left, from a lowest power to the highest power or vice versa. Can we not use arrays for representing this sparse polynomial? It is possible. For example, you can have an array of structures where the structure is similar to what you have inside the node of a linked list, where you have two variables. One is coefficient, another is power. And then the index doesn't mean anything. It's just that you are actually storing the power also along with the coefficient within the array. So the array elements are going to be exactly the same, -1, 1, and 2, 1000. So this is how you will represent it in the array also. So that is also possible. It's just that we are not going to get any advantage of that index. So that is something which we should be aware of. So it's not necessary that this has to be done using a linked list, but it comes very naturally. There is an advantage of this, which will become clearer as we get into adding of polynomials, because then you'll be probably inserting something in between. And we know that for arrays, array insertion is going to require order and operation if we have to shift elements. Whereas in this case, it is probably going to be, in case of linked list, it is going to be much easier. Once you know the points, then you can insert in order one time. All right, so the design decisions essentially are going to be based on the member functions that we have. And like one of the concerns was whether to store it from left to right or right to left, right? So that could be one design decision. There could be other design decisions. For example, you might allow certain powers to be present or not. For example, you might not allow negative powers, or some people might allow negative powers, and so on. So all of these will come into picture. But you should also think about, as you have probably created this offline classwork and you have implemented this structure, please see if what are the other design decisions that will be required in this case, right? The design decisions also, as we have seen, need to be guided by the complexities of these functions. And those complexities are essentially going to play a role when you are thinking about operations on these polynomial ADTs. And the operations are essentially these member functions, but more importantly, operations on polynomials, which are going to be adding of polynomials and multiplication of polynomials, right? In our case, right? And if you have other functions which you want to define, then those are going to also play a role. All right, so assuming that you have done something like this, I can think about a coefficient array, which is going to have the maximum degree possible, right? So in case of arrays, I need to specify this bound, which is going to be the maximum degree possible for any polynomial that you are going to represent. This max degree could actually be very large. I mean, you might want to support, okay, I don't mind having tens of thousands of power for x, and I can represent that. But the actual polynomial that you are storing could actually be very small, and in which case we are going to waste a lot of memory. But anyway, if we have decided that arrays is going to be the base underlying representation for polynomials, then so be it. So that requires all the coefficients which are going to get stored, and the index is going to tell you what is the power of x. And since I have written it directly without any public private, that means that in C++ there is going to be private variable. And then that means that only the functions which are going to be inside polynomial, those are going to be accessing those. So don't think that this is a completely valid code. This is almost like a pseudo code, just that because we have to add member functions also. So I'm just showing only the relevant portions, and you should implement all of this. Initialization is could be that you are initializing with all zeros. That could be one. Another could be that I actually provide you all the powers for initialization. So essentially, I am providing the polynomial itself, right, in the coefficient form, and you just take this coefficient array, and you are going to initialize your coefficient array inside the class with this, right? So because the parameter that is being passed to initialize, right? So this parameter coefficient is a local variable to initialize, right? It's being just passed, so it's a copy of the pointer, but you would like to store that, right, inside the class so that other functions can make use of it. So therefore we'll have to store it, right? So there is going to be one small syntax based non-triviality that is going to come into picture if you try to implement this, and I would like to I would like you to figure that out. Some of you would know what the problem is, but if you type this signature and have this class and the variable inside that coefficients array, then you are likely to face that difficulty, and hopefully that will lead you to something interesting. Okay, I'll leave that to you. But essentially, this is going to require you a for loop, and within that for loop, we'll have to initialize this. The small issue here, and again, as I was saying, that this is not the exact code which you should be using, because in this case, you will also require the size of this array which is passed, or you can use max degree. You can assume that this coefficient array that is being passed is also max degree plus 1, and therefore you can just go over the loop like that for I equal to 0 to max degree plus 1. Right? So please take a moment, pause the video, and try to implement this in your notebooks or online. Okay, the second function that we talked about is, or one of the important ones that we talked about, is the addition of polynomials. Now, what do you mean by addition of polynomials? You have this polynomial 1, polynomial 2, and whatever are the common degrees, their coefficients get added. Right? The coefficients could be positive, negative, 0. Now, this becomes very easy when we are implementing it using an array, because I precisely know what are the coefficients and what index they are in. So you have two arrays, essentially coefficients arrays. So in this case, note that polynomial P1 and polynomial P2 are being added, and the result is going to get stored in another polynomial P sum. One question that will come up is, where is polynomial P1? And how you are going to call this particular function. Right? So that is also something which you should think about and try to find that out. I'll explain this. If maybe you can pause the video, think about it, that you are able to understand the difficulty that polynomial P1 is missing in this signature. P2 and P sum are present, and these are two different instances of the same class polynomial. There is another small issue with respect to this, that the way I have defined this P2 and P sum, these are copies of the P2 and P sum variables that are probably being passed as parameters, and therefore these may not be able to reflect the changes which you do inside this add in the caller, that is main. Right? So you should be careful while passing these parameters also. These I have just mentioned, as I was mentioning, this more, think about it more like a pseudocode or just some snippets just at a high level, but this is not the actual code, which means that you have to probably pass maybe pointers. So I need to probably specify as polynomial star P2, polynomial star P sum. Alternatively, there is a provision in C++ to pass variables by reference. This is not available inside C. So you can specify polynomial ampersand P2, polynomial ampersand P sum. And then whatever changes you make to P2 and P sum, those will be actually reflected in the variables in the caller. Otherwise, if you just pass those as by value, the way I have done or I have shown, that is not going to get reflected. These are just copies of the variables which are present inside the main. All right. So where is polynomial P1, right? So that is the question. And how you are going to call this particular function. The way we have to call this function is going to be, so think about it, okay, we'll think about it from the initialize perspective first. How are we going to call initialize? So we are going to say polynomial P1 and then P1 dot initialize. Right? So this is what we are going to write as the main code. Right? The way we did for lists, where we said list L dot insert and then some character. Similarly, in this case, we will say polynomial P1 and then P1 dot initialize, and I'll pass some array which contains all these coefficients. Now, when I am inside initialize, which coefficient array I am updating? I am actually updating the coefficient array of the underlying object. What is the underlying object? The underlying object is on which initialize is called. So P1 dot initialize means that initialize is being called for P1, and I don't have that P1 as a parameter to initialize. That is kind of implicit to initialize. Whenever I do P1 dot initialize, it calls initialize on P1 itself. In a similar manner, when I am calling add, it has to be on some polynomial. And in fact, in this case, I am going to say P1 dot add, and therefore P1 is implicit into this. So when I access COEFF coefficient array inside add function, I am going to access P1's coefficient array. What if I have to access P2's coefficient array? I'll say P2 dot coefficient, assuming coefficient is a public element. If it is a private element, then I need to query, I need to provide an API in polynomial which will take an index and give me the coefficient of that index. So then I'll have to say P2 dot get coefficient, and I'll pass I as a parameter, and that ith index it will return, the value in that index it will return. In a similar manner, if I have to set the value inside psum's coefficient array, then I need either coefficient to be public, or if it is private, then I need to provide a setter function which will say psum dot set or some set coefficient. I pass two arguments. One is I, that is the index, and the second one is value at that index. And accordingly, psum will get updated. That particular index will get updated. So those functions are going to be auxiliary functions which are going to be required for our polynomial to work out. All right, so I suppose the difficulties are clear, and where is P1 polynomial, that should also be clear. So therefore, from main, I'm going to have polynomial P1, comma P2, comma Psum. The names need not be the same, but I'm just taking it for the sake of convenience. And then I'm going to say P1 dot initialize something, P2 dot initialize some array, and then P1 dot add, and the two parameters that I'm going to pass are essentially P2 comma Psum. So if you are taking it by polynomial ampersand P2, polynomial ampersand Psum in polynomial colon colon add, then I just need to pass P2 and sum. If you are going to have polynomial P2 and polynomial Psum as pointers, then I need to pass ampersand of P2 in main and ampersand of Psum in main as well. Just a minute. Okay, so the classwork currently is that we have to implement this particular add function, right? So we just talked about only the some of the C++ related aspects, but there are computation related aspects which are going to come, but essentially those are going to be relatively easy once you have the coefficients array, right? So the underlying representation is an array, so that should be easy for you. Just a for loop should suffice in this case. Again, you have to decide how much is the array length, right? So if you always go for max degree, that might actually be very large. So whether you want to store the max degree inside the polynomial, that could be one way in which you can think about improving the execution time. The complexity may not change, but the the complexity will probably change as well, because you can now talk in terms of the number of non-zero element, the number of the max degree that is present inside the polynomial rather than the max degree that is supported in the implementation. All right, and these two are different variables. Okay, so all looks good so far with respect to the array-based implementation. Oops. What can we do when you have a list-based representation? So the coefficient array that we have, that is going to change now to have a head pointer, which could be of some type node star or something similar to our linked list. And then I don't need to worry about initializing it. It's just, initializing meaning allocating memory initially. It will just be a null in the constructor. When I'm initializing and passing the coefficients array, at that time I need to create that list. Again, those many elements, and exactly possibly the ones assuming that you are having a sparse representation, you are not storing the intermediate ones, which the non-zero coefficients are not getting stored. Sorry, the zero coefficients are not getting stored. In that case, you will just have those nodes being present. That will be our initialization function. When you are doing the add, as far as the caller is concerned, that is main is concerned, your syntax doesn't change. It will still be p1 dot initialize, p2 dot initialize with certain parameters, and then p1 dot add p2 comma psum. So this representation is not changing, despite the underlying implementation changing from array based to linked list based. So that is a good point. But then the implementation that we would like to do for the add is going to be very different, because now you are going to have only the sparse representation, only the non-zero coefficients are present, but those are not indexed. So the first element of P1 and the first node in P2, these may have different powers. So this is going to require you to have some sort of merging, right? So we did merge of linked lists in the or merge of arrays initially, right? Where you have two sorted arrays and you would like to merge those. So that learning from there will come in handy here, where we'll have to look for which one is the next one to add and then update in psum. So we have to go over P1's list as well as P2's list, and only when the powers are the same, then only we have to add those. Otherwise we have to see whichever does not have the other power present, just take the one which is present and add it to psum. Right? Here we will again assume that psum is going to be empty, that is the head is going to be null, and then you have to call some function to insert a node of a particular degree, right, having certain coefficient value. Right. So this is going to be requiring you to traverse both P1 and P2 in a particular way. Why did I compare this with the sorted array is because there was an underlying assumption that I made that the powers or the coefficients of powers are going to be in the same order as the nodes, right? So degree 0, degree 1, degree 2, degree 3, like that we are going to store, but that is not really necessary. One might decide to have a polynomial ADT such that the powers are arbitrary, because I'm actually going to store the power. So I don't have a compulsion that it has to be sorted in the orders. Right? So degree 0, degree 5, degree 100, right, in a sparse representation. That need not be in that order. I can have 5, 0, 1000 degrees and accordingly coefficients. But when you are adding these sparse representation lists, at that time this sorted nature will come in handy for you, and you will get a better time complexity. By default, the complexity is going to be n square, assuming that there are n nodes in each of the two lists. It's going to be n square, because for each node here, you will have to look for that particular degree in the all of this. That can take order n time. But if it is sorted, then you can merge this in order n plus n time. And therefore, you will be able to do it in linear time with respect to the sizes of these lists. So that also is a design decision. If add is a very frequent operation onto the polynomials, then you might want to optimize add. If add is not a frequent operation, then you don't need to even worry about keeping this sorted, and maybe make other operations faster. So again, I'll leave you with this particular implementation of list-based ADTs, right? So in Wies's book, we actually have the implementation using lists, and therefore I have thought that on the slide I'll show you the representation, at least some summary of the representation using arrays. But I think it's worth spending time in implementing this, so please try that out. Okay, so this list reversal part we have already kind of covered in the when we were going through the code, but I'll just quickly go over this for the sake of completeness. So you would like the head to change from whatever be pointing to the first element to the last element, and the links also need to get reversed in the reversal. Given list, how do you reverse? There are multiple algorithms, and the algorithm that we have used is a recursive, nice formulation. You can do it iteratively also, where there are two pointers present. Right? So the current one and the next and the previous one, especially for a singly linked list. And then while reversing, you just make the current point to the previous one after making some pointer go to the next one. And this you go on doing till you reach the end, and that gets, and then you change the head to the last one. So that is one way in which this reversal can be done. But there are other ways. For example, there was a recursive formulation that we said is that I am at a current node. I'm going to call recursively for the remaining list. As long as it gets reversed, I get the tail of it. Right? The tail of it. And then this particular node needs to be added to the tail, because this node was initially before the list. Now it should be at the end of the list. And then the new tail I need to return, and so on. So this is what we did in case of a recursive formulation. Right. Yeah, so this is, but this can be done for all the other lists also. For example, for singly linked list and circular singly linked list, this makes sense. The order is going to get reversed. But what about for doubly linked list? So doubly linked list already has the, you can go in previous direction also and next direction also. But the reversal in case of doubly linked list can mean that when you are traversing it using next pointer, the order should get reversed. And same for the previous one. And therefore the same thing should be applicable for CDLL also. So we have the code, but I recommend that you try to write it on your own. Maybe we have the code only for SLL, and you might want to try it for other types of lists. Okay. Yeah, so this is what we might require. Yeah, so that we have already seen, but you can try doing that because it's a little, I mean, you can do it iteratively or recursively, but you can make mistakes, especially with respect to the end cases. So you might want to be careful on that part. And this also we have done. So like we have done iteratively, we have done it recursively also, but just wanted to mention that sometimes, I mean, when you think of many of these data structures in as a recursive formulation, the operations on them can also be very naturally modeled as recursive. And that's what we did with respect to lists, that it's either empty, that is the base case, and the inductive cases. Otherwise, it is one node followed by the rest of the list. I can as well model it in a different way. For example, I can say that either it is empty or it is n-1 node list followed by a tail. That is also another recursive representation of a list. And if that is the case, why can't I represent an array as a recursive manner, right? So either array is empty, which is usually not the case, because you cannot declare an array of 0 size. You can declare only a pointer, but you cannot declare like malloc 0 will give you some pointer which is not pointing to anywhere or something like that. That is probably not, doesn't make sense in the representation sense. But let's say that we say, or the base case we change to an array is at least one sized element, or it is one sized element followed by some n-1 elements, or the opposite, that n-1 elements followed by an element. So this is also a recursive formulation of an array. And as soon as we define it this way, I can process the array in recursive manner. So we have to find, for example, a maximum element in an array. I can say that the maximum element is either the first element, right? Or if in the base case, right? So when it is having only a single element, it is the first element. Alternatively, I mean, when in the inductive case, when there are larger number of arrays, it is take the maximum of n-1 and max of these two elements. So these two are two different maxes I'm talking about. One max is on the whole array. Right? So let's call it max array. So max array of n-1 elements. And then there is a max 2, which is keeping track of which finds the max over just two elements. That is the first element and whatever max you have obtained from the remaining n-1. Right? So this itself becomes a natural recursive definition of max once you define the array in a recursive manner. In a similar manner, our lists also, which are anyway very natural, and slowly we'll see that almost all other data structures that we are going to study can be naturally modeled in a recursive manner. We can define a max, for example, in this case, that if the list is empty, then the max does not exist. If list has only one element, then it is going to be that particular node's value. Or when you have a larger list, then you can say that it is going to be max 2 of the first element and max list of the whatever head arrow next. So that is going to give you a recursive definition of max over a linked list. So many of the other operations which we do that can be naturally modeled as recursive methods. So I just wanted to highlight that here. Recursion typically is assumed to be, not assumed to be, but typically turns out to be inefficient because you need to maintain multiple memory locations for storing the context information as you go from, let's say, one invocation of the function to the second one, to the third one, and so on. Right? So when, for example, you might think about implementing Fibonacci number, nth Fibonacci number, or even factorial of n. Right? So all of these can be naturally modeled as recursive functions, and when you try to implement those in that natural manner, then you will see that it takes a large amount of time compared to the iterative version. So therefore, there is that inefficiency might come into picture. There are advances in compilers using which some special forms of recursive functions can be implemented in such a way that the efficiency is exactly same as an iterative version for large values of n. So that is possible, but that is only for a limited set of recursive functions. By and large, you will have to model your computation iteratively to get that efficiency. So in case of lists, and we can initially start from singly linked list, then go to other variants of the linked list. That can you identify an element? Can you find an element? Can you search for an element recursive? So that also can be very nicely modeled. Once you have that thought at an abstract level in a recursive manner, you'll be able to implement it quickly. That is, if I'm searching for an element, if the list is empty, the element is not present. Otherwise, the element is going to be either the first element if it is the same value as you are searching, followed by a Boolean find versus not find of the remaining list with respect to the current node. Right? So the current nodes find and the remaining lists find. You combine these, again similar to the max. There are two versions of max here, two versions of find here, where the find is about the n-1 elements in the list, that is the remaining list, versus the, let's say, an ORing operation which is happening with respect to finding on the current element and the remaining set. I mean, whatever you have obtained as the result of the remaining set of elements. So can you write this in an iterative manner is the question. Please try that out. Similarly, you can actually print a list recursively, and this we actually have seen, and even the find we have seen recursively. So just go through these codes after trying for yourself. And we also observed that in case of printing a list, just exchanging the two statements changes the order, and that can turn out to be very useful. Contrast it with an iterative version to print a list in the opposite manner. Yeah, so that is what we have seen. So stop here, and in our next class we'll do stack abstract data type. See you. If there are any questions, feel free to post on Google group. See you.